from this correlation. Okay. So this is the data set that I'm actually going to use to explain some ideas about linear regression. Okay. Um, Correct. Correct. Absolutely. 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 So all of them are relevant variables. I'm not saying they are not relevant, but using only one of the easy to measure variables, there is still some progress I can make. That's the claim. And in business situations, that's exactly what is going to happen. You do not have all the relevant variables that are going to be there, that are relevant to making some future. But you know what? They're going to make demands on you saying that I want you to give me a forecast. Okay. We are doing one such consulting problem for one auto company in Japan. They want us to forecast how many products are going to be sold. Um, they do not give us information on what that product is. They just give us information on for 3 years. This is the amount of product that has been sold. Okay. I want you to forecast how much I should stock for next month. So we asked them, okay, can you give me the sales of the original car for which these parts are used to? Sorry, we can't give you that. Can you give me the value where the sales happen and how many competitors are there? Sorry, we don't have that information. Sometimes there's only limited amount of information. The question is, what can you do? What can you forecast with that limited amount of information? This method gives you one way, and sometimes it works, sometimes it won't work. But we are going to consider this one particular example and analyze in detail in this one for this particular example after this. Yeah. residuals are smaller, R square. They just happen to be. Residual sum of squares divided by total sum of squares. That number has to give better when the ratio is smaller. So 1 minus that is R square. Percentage of error is what you 1 minus percentage of error. Percentage. Because yeah, because a simple example. You are measuring how far car is going. You are measuring given time how much distance is it. So time is here. So you're talking about so many minutes. You're talking about meters, how many meters. So the graph looks here. So your correlation coefficient will be y minus I mean the summation of all those. Let's say this number turns out to be this now suddenly instead of using meters, you decide that I'm going to use millimeters. Fine, and you should still have the same information. No one says you should use this. When I use millimeter, all numbers are multiplied by 1000. So it means this number is going to be multiplied by 1000. So it's even more large. But it's the same pit. So size of that does not indicate anything at all. However, look at correlation coefficient. It doesn't matter what the units are. It will always be correlation. Correlation R and R squared. Oh, how? Where was this? Where did we get this data from? Okay, so here. So here. This. Right. Yeah. So these should represent the same value. Same material. So value is value. So this really should be the exchange rate. Right? Really, this should be the exchange rate. Because for the same amount of money, you get the same goods. That is what the exchange rate should ideally be. So I take this number and divide by that number. I get 31 rupees per dollar. So really, for $1, it should cost only 31 rupees. Right? But actually, dollar is 67. So you're getting half the amount of dollars. So your currency is undervalued. Indian currency is undervalued. It should actually be 30. What state purchasing on that? So this is one of the things 30 years back. This suddenly changed. They used to live country per capita. And India used to see that at the bottom. And then they realized that He's not poor, no matter what the dollar of conversion. So you idea for purchasing power value. So how much is the amount purchase using your, and they use that amount to compute the actual. When they use that, then the actually came out high, pretty high in the instead of whatever I can give. So shipping power value tells you that instead of actually 31 is actual price of dollar. So our rupee is undervalued. So what you are saying is, yeah, from the mean when it moves uh, one unit from the mean, then from the x it's moved that many units. The way, so there is. Let me put some numbers. We are going to do one explicit computation, and it'll be clear. Yeah, yeah, yeah. But the come to me if it is not clear in the head. Okay, if I forget to answer that question, come to me. Okay, so we're going to continue with this Big Mac problem. I will use this as a data set to explain ideas about best fit of regression and so on. As I mentioned, there are a lot of different types of analysis one can do using this particular data set. Okay, I'm going to choose one of them. The one that I'm choosing is looking at the net hourly wage in different countries where McDonald's are there. Okay, so what I'm showing you here is the price of Big Mac in variety of countries on the x-axis, and on the y-axis I'm showing you the net hourly wage in that country. Okay, net hourly wage in that country versus the price of Big Mac. What would your expectation be if a country, McDonald's is a logical company, if they can charge high price for their burger only if the net hourly wage is also high, right? If the net hourly wage is low in that country, it automatically also means that it's cheaper to produce goods in that country. So bread is probably cheaper, meat is probably cheaper, whole bunch of things are cheaper, and so they can afford to sell the burger at a low cost in that country, right? So one would expect these two numbers to have a relationship: the price of Big Mac and the net hourly wage, right? When you plot them, you do see that as the price of Big Mac increases, the net hourly wage number also seems to be higher. Okay, I am not saying that the increase in price of Big Mac is causing the net hourly wage to increase. I'm not saying that at all, right? I'm not implying that one causes the other. I am just saying there seems to be a relationship between those two. Yeah. And what's nice is that this relationship can be explained to a reasonable level with a straight line. And you know what? The R squared for this. So this is the best fit line that was done in Excel. It gives y equal to 3.54x minus 4.154. That's the equation of the line. The r squared is actually 51%, 0.51. Okay, is that number high or low? Depends is the correct answer. Okay. Whenever you don't know, just say depends. In this case, it's actually appropriate answer. With r squared, there is no higher numbers are better, but there is no threshold as this is a good number and this is a bad number. So that was the correct answer. It depends on the domain you are talking about, whether that number is high or not. Let's specifically talk about here. In this domain, we are saying using the price of Big Mac. Okay, I'm giving you the price of Big Mac in Czechoslovakia, and I'm asking you what is the hourly wage there. You look at the price of Big Mac, and from there you are saying the hourly wage is probably this particular number. You are able to say that without knowing anything at all about the labor policies of that country. How big is that country? In fact, where that country is in the map, right? No information you're using, and you're able to say that. And this variation in the net hourly wage, you are able to explain with Big Mac with r squared of 51%. So 51% of variation in hourly wage can be explained just with the price of Big Mac, right? Economy is a complex thing. Whole bunch of things go in determining the hourly wage. The fact that we can determine that, explain 51% of the variation with the Big Mac price, when you put it in that context, this is a pretty darn good number, right? So it depends on the context. It depends on the context. You're not saying this causes that, but you're saying I'm able to explain 51% of its variation just with this. Okay. So this is what we are going to do is we are going to that's a very good question. So did you understand the question? Right? So I'm saying 51% is explained by this. Does it mean that 49% is explained by all other variables? So perhaps, does it imply that all other variables are less important? Right? Because it's less than 50, right? All other variables combined is less than 50, meaning this is the most important determinant. It doesn't mean that. However, you might find that, for example, you can get the labor policies and quantify that into a number, and you put that on the x-axis and put the net hourly wage on that. That might by itself have 60% variation. So it doesn't mean that the summation of all of this should be equal to 1. You are just saying this alone can explain 60% or this alone can explain 50%, but these two might be correlated among themselves. Yeah, we will come to that point. That's a very excellent question. We'll come to that point tomorrow. We'll talk about the subtleties involved in that. It is not that either, and that specific question we will address again. What is the probability of me being correct? That we'll talk about. We essentially are asking about the error range, right? And we'll come to that in the next slide. R squared, the only thing it tells you is, instead of making a simple prediction of mean, which is an easy prediction to make, okay, from that level, how much have I improved by adding this one variable? That's what R squared is telling you. Okay, percentage of variation explained by this set of variables that I'm looking at. I can put this in R. Let me do that. Sorry, in Excel. So I have this data of Big Mac price, net hourly wage. Okay, I'll show you how to do this linear fit on Excel. I am marking these two columns. Go to data, choose data analysis, and in data analysis you see plenty of options. You see ANOVA, correlation, covariance, so on and so forth. I'm going to do regression on that. Click OK. Input Y range is this. Input X range is that. And I say both of them have labels, and I'm asking it to input there. So I have an output that looks like this. So what it says, I want to first draw your attention to things in the bottom here. I don't know whether these numbers are clear. Let me just go to switch to PowerPoint. Larger font size. Okay. So on the bottom are it's the best fit values. It gives you the value of the coefficient multiplying the Big Mac price is 3.54 and the intercept is minus 4.15. That's what it says. Okay. So what is the equation of the line? Y equal to 3.54 times the Big Mac price minus 4.15, right? This is what you would write. Okay. Now let's look at other numbers that are being printed, and we will analyze what all of these numbers that are being printed. What is the meaning of that? Okay. Let's start by looking at the values next to the slope. Okay. So 3.54 is the coefficient. Okay. I mentioned that this coefficient is the estimate of the population, the mean value of the slope of the population. Okay, it's an estimate of that. That's what it is giving you. Okay, if it's an estimate of that, then it means that there could be errors, right? We are acknowledging it's error because we are analyzing this based on a sample, right? That quantification of that error is given here. This is the standard error. This is a term that you have already heard this before, right? The standard deviation of the sampling population of the mean is standard error, right? So this is the standard error. In addition, you see the t statistics, right? What is this t statistic telling you? Now, without knowing anything, before we talked about this underlying logic, if I had asked you this question, is the price of Big Mac, is that going to be determining factor for the hourly wage? What would your answer be? Correct. You would have said unlikely. Okay. In fact, given any two random variables, the chances of those two variables being connected it's unlikely, right? So what would the slope be? Expected value of slope would be 0, right? This is the null hypothesis for the regression problem. For the regression problem, the null hypothesis is that the variables that you are analyzing are not related and the slope value is actually 0, is the null hypothesis. What is being measured here? The fit, it gives you one slope for the given data. It also gives you what is the standard error. How do you compute, given the sample mean, how do you compute the t-statistics? T-statistics is your sample mean. So sample mean minus the population mean divided by the standard error. Correct? What is the population mean here? The null hypothesis. Null hypothesis was 0. So this is this number divided by standard error, right? That should be my t-statistics. T-statistics is computed here as 5. So it is actually saying you are about 5 standard deviations away from the mean. Is that likely or unlikely? Unlikely, right? So the p-value, the chance of this happening is 2 times 10 to the power minus 5. It's unlikely. What is the threshold we normally use for deciding whether it's to pass the hypothesis or not? 5% significance level. This number is much smaller than 5%, right? So what we say is it's unlikely that the population mean is 0. So we reject the null hypothesis. So what this p-value is telling you is that there is a connection between the Big Mac price and hourly wage. You cannot say that it's 0. You can reject the null hypothesis. Okay. So that is where that is the whole reason why we did all of those 5 classes of statistics. Now you see where it's connected. This probability value tells you whether to actually take the output number that is given seriously or not. Is there truly a connection or not? That's what it's telling you. Is the idea clear? You want me to go through it again or you're fine? So the idea is we analyze this method is familiar to us of analyzing statistical statements using hypothesis testing, right? The for hypothesis testing, the structure is always there is a null hypothesis and alternate hypothesis. The null hypothesis in this case is that the given two variables are unrelated. If they are unrelated, the slope value you get should be 0. Okay. There is no reason to expect any connection at all between two random variables, right? So it's a reasonable null hypothesis to start. We will reject the null hypothesis only when the evidence is very strong. Okay. So it is giving me a slope value. But then this is Excel, right? You throw in any set of numbers, it is going to always give you a slope value. That doesn't mean the slope value is actually telling there is a connection, right? To understand whether it's telling you a connection or not, you look at the standard error. Okay. So it gives you the slope and the standard error. So standard error is a measure of uncertainty in the slope, right? Using that, we can compute the t-statistics. T-statistics is nothing but the sample mean minus the population mean divided by the standard error. Population mean is your null hypothesis mean. If null hypothesis was true, your population mean is actually 0. So use this slope, sample slope divided by standard error, you get you the t-statistics. T-statistics is essentially telling you how many standard deviations away from the mean you are. In this case, you are 5 standard deviations away from the mean. So it's highly unlikely that the null hypothesis is true. So this p-value is telling you that this number is something that you should take seriously. It is definitely not 0. Okay. So the slope has significance. That's what it's telling you. Now let's look at the next number, intercept. Intercept in this case is minus 4.15. Standard error for the intercept, it's computing to be 2.44. T statistics turns out to be 1.69, right? If you look, you can look it up in the probability tables, the T table, or in this case, it conveniently gives you the p-value. What does the p-value say here? 10% chance. So can we reject the null hypothesis? 5% is the threshold we keep. So we cannot reject the null hypothesis. What was the null hypothesis? That the intercept is 0 is the null hypothesis. In this case, it's saying I'm not able to reject the null hypothesis. So it's very likely that the intercept is actually 0. So the equation of the line, I have no reason to believe this number should exist. So the best fit line for this problem is just y equal to 3.54 times the big max line. That's the best fit line. Excel happily gives you an intercept and slope. But you need to decide which of those values you should take seriously. It gives you enough background for you to decide too. It's telling you what the standard error is. It's telling you what is the probability of that value being true. Right? So in this case, this p-value is very small. So that means that is a significant coefficient. You should put that in the equation. This one, p-value, does not cross our 5% threshold. So we should ignore that coefficient. That is adding that does not make any sense. So actually we leave out the slope, the intercept value. Is the idea clear? Yeah, p-value, it's just giving it for completeness. But on a practical term, to decide whether the intercept and slope are significant or not, all you need to do is look at the p-value. Now, lot more information is contained here. We talked about this whole hypothesis testing formalism and confidence interval formalism being the same. You can get the same conclusion. Yeah, sorry. Correct, yeah. So, we always start, this is why we did the hypothesis testing first. We always start with the null hypothesis as being the most likely conservative hypothesis. Most likely to be true. Most likely to be true is two random variables that you are giving is unconnected. So, there is no reason to believe there should be an intercept. You don't have strong enough data to say that there should be an intercept. That's what it says. So, why would you put an intercept? Correct. So which means the equation you need to look at is only this. That's the equation for the line, best fit line. So correct. Good. Yeah, the two-tailed test or this thing. In this case, we are saying null hypothesis is 0. We don't mind a slope being negative or positive, as long as is it sufficiently away from 0 is the question. So it's actually two-tailed test we are doing, and the p-value is actually computed for the two-tailed test. Yeah. Good question. There will be. There is. It depends on the data set you are giving. Excel will happily go ahead and compute all of these. Ultimately, you as a data scientist need to decide which are the coefficients that are relevant, which are not the ones, which are the ones that are not relevant. So, in this case, what you are trying to do is you are asking the question: is Big Mac prices an explanatory variable for the hourly wage? That is what you are trying to find out, right? So essentially, the question that you are asking is the, the slope for the Big Mac price, is that actually relevant or not? Okay, that's what you are asking. And in this case, it does turn out to be relevant. The intercept, there is no reason to believe the intercept is any different from 0. But the slope is something that you can believe. That's what it is. Yeah, correct. Right. All right. So the very good. The null hypothesis is actually stated separately for slope and each one of the coefficients. Now there is, so separately for the slope, the p-value is very small, so slope is significant. You should believe the slope. The intercept is not significant, so do not believe the intercept. Now, in addition, it's actually giving you more information. We will look at the previous column, the previous information. Do you see another number over here that's familiar? The F statistic. The F statistic, what that tells you, it's actually the output of ANOVA. What it's doing is this. ANOVA analyzes, what did we use ANOVA for? We had different possible data sets, and we were talking about, are the mean of those data sets all the same, or is any of them different? That is what we used to analyze, right? Over here, ANOVA is actually analyzing given the independent variables. In this case, we have only one independent variable. Big Mac price is the only independent variable. But generally, this is applicable even if you had 5 independent variables. Generally, for the 5 independent variables, is the slope all equal to 0, or is at least one slope non-zero? That is what ANOVA gives. So this F value is actually telling you, of all the independent variables that you gave me, is there any intelligence at all in them? Is there a reason to construct a model at all? That's the conclusion F statistic will let you make. So when you look at the F value, what does it say? The significance of the F value is 10 to the power minus 5. Is it in the critical region? It is in the critical region. So that's telling you the null hypothesis that all of them are 0 can be rejected. There is some intelligence in your data. There is a reason to go trust your model. So the way you should do is, the way you should analyze results of regression is first look at the F statistic. It tells you on the whole, does your model have intelligence? If this number is smaller than 10 to the power, smaller than 5%, then you say that the model has intelligence. Now let's look at which are the coefficients that are relevant. Now you look at the coefficients and you see that, well, the slope is relevant, but the intercept is not relevant. So we will keep only the slope. Intercept we have to reject. Yeah. Correct. 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 Absolutely right question to ask. 95 is just what is chosen by convention. But let's think about if you had chosen 99%. 99% confidence interval, meaning what is your significance level? 1%. Let's look at 1%. Does this pass? the slope passes. 10 to the power minus 5, right? It's definitely passes. What about the intercept? Intercept is at 10%. So intercept doesn't pass. So when you reject at 5%, it will also be rejected at 1%. The stronger case you make, definitely is the threshold for acceptance is much higher. Yeah. That's a domain decision you need to make. Convention is 5% significance or 95% confidence. Okay. This information is telling you does your model has any intelligence or not? Is the model even valid? Or is all the data points completely random? In this case, it says yes, the model is valid. Then you look at which variable is actually significant, because ANOVA analyzes all the variables together at one shot, right? So this is telling you yes, there is something that is different, at least non-zero. There is at least one thing that is non-zero. You go down and you look at which one is non-zero. The slope is actually non-zero, so you take that. The intercept, there is no reason to believe it's any different from zero, so we leave out the intercept. The plotting of the graph, the line would slightly change, because when the intercept changes, the line moves along like that with the same slope. So when the intercept is 0, now the best fit line actually goes through the origin. So essentially, you will say that when the Big Mac, the country where Big Mac price is 0, the hourly wage is also 0, is what you would say from that. Yeah. Correct. Correct. Right. Correct. Right. So plotting of the line, this is why R does not do it automatically. It makes you do it separately based on your domain knowledge and knowing whether to which one to leave out, which one not to. So the fit is the lines, although I'm showing, that's a separate command I give in making this plot. And at that time, I need to choose whether to put the intercept line there, intercept or not. So in the case of simple linear regression meaning only one independent variable. Okay. In the case of simple linear regression, if the slope is not significant, the model also will not be significant. Okay. You might notice that the p-value for the slope is exactly equal to the p-value, the significance value of the model, right? And that's to be expected. I mean, there is only one independent variable. If that independent variable is not significant, the model has no meaning at all, right? In multiple linear regression, where there are multiple independent variables, it is possible that the model is significant, but not all of the independent variables might be significant. You need to decide, look through and decide which independent variable is actually significant, which one is actually contributing to explaining the model. So you need to do that separately. Correct. So we also noted that, truly speaking, P is the right number to consider. Even when you have large samples, P will immediately coincide with the Z value. So safest to always look at the T statistic. We introduce Z value because it's intuitively easier to understand the Z statistic. But T is the one to be always be looking at. And that's why all of these softwares also produce T. Yeah. Maybe, may not be. This is separately evaluating, does the data support a value that is distinctly different from 0? That's all it's they're trying to say. We will do an example where you will see that these two might be, they're giving you slightly different information. The slope value, okay, now that you referred to correlation coefficient, let me explain the numbers that are over there. The first number over there is R, that is the correlation coefficient. That's at 71%. Second number is R squared, which indicates which is the coefficient of determination, or it indicates the quality of fit. That number is 51%. So 51% of variation in the hourly wage can be explained just by the Big Mac price. That is what that number is telling you. We'll forget about adjusted R squared for now, and the number of observations is 27. I'll explain what standard error is in just a few minutes once we get down to actual computation. But this might be an appropriate time to do this portion of the output. What this is giving you is, we talked about coefficient is the mean value from the sample is giving you the standard error. From those two, you can compute the confidence interval. How do you do the confidence interval? So if it is 95% confidence interval, then you do 1.96 times standard error plus or minus that number, right? That gives you the 95% interval, right? That's what they have given. The lower 95% of the slope, upper 95% of the slope. Does this number include 0? This number does not include 0. So with 95% confidence interval, I can tell that it is not 0, right? So this information and this, both of them are giving me the same information. The hypothesis testing formalism and confidence interval formalism, both are equivalent. They won't contradict each other. If your domain requires you to analyze at 99% confidence, then it gives you these numbers. And of course, at 99% confidence too, it doesn't include 0. However, look at the intercept value. The lower 95% is -9, upper 95% is 0.8. And this range includes 0, right? So we cannot say with 95% confidence that the value is any different from 0. And that's another reason why we are ignoring the intercept coefficient. Questions? So this is going to be the longest slide that we'll be spending time on in both the modules. So the time spent on this is worth it. So please do let me know if there are questions. Yeah. Our output is also going to be similar, and we will come there in just a bit. So lower 95, the way we compute 95% confidence interval, margin of error is the p-value for your threshold times standard error. Okay, that's the margin of error. 95% confidence level, this value is approximately 2, plus or minus 2 standard deviation, right? It's approximately there. So you take this number plus or minus 2 times this standard error. So this is the mean, sample mean, minus 2 standard errors, sample mean plus 2 standard errors. That will give you a 95% interval. That is these numbers, 2.12 to 4.96. Okay, and this number, this interval does not have 0 in it. So with 95% confidence, I can tell that this slope is different from 0. So we are saying slope is significant. Yeah. Sorry? 2 times standard error, because you remember 95% of the area was covered in plus or minus 2 standard deviation from the Z distribution. Z distribution really is valid only for samples that are for large samples, right? But as the sample size approaches 30, T distribution starts looking like Z distribution. Over here, our sample size is 27. So it must be near 2. Yeah. You can use any one of the values. I'll tell you what I use. What I always use is I immediately look at the p-value. I look at the p-value and make the decision. So, and that has same amount of information. Why do they give you this? This is sometimes needed in a business context. You might need to provide to your client what is the level of uncertainty in your slope. So then you they are giving you this value so that you can give your client, this is the uncertainty in the slope. So this is my best fit line for the given sample. But if there was a slightly different sample, it might have been, the slopes might have been slightly different. And you're giving you the range of that slope. Okay? Correct. If the slope happens to be not significant, then the model will also have the same p-value and the model will also not be significant. So you just throw out this linear model. You say that these two data points are not linearly related. So you throw out the entire model. Yeah. Good. So there is one more important part in analyzing output of regression. First important part in analyzing the output of regression is, I showed you, given the two data set, how do you get the best fit line regression? I showed you mechanically. This is what most people do, mechanically plot it and submit the output. Okay. We have learned something extra in that output cannot always be trusted. You need to look at it and carefully analyze which values are significant, which values are not significant, right? We spend time on that. In addition to that, there is one more thing that you need to look at before you submit your result to your client, and that is called residual analysis. What is residual analysis? Do you remember what residuals are? Errors, right? Actual value minus forecasted value. Actual minus fitted value, right? That is called as residual. What I'm doing here is I'm plotting the residual. So residuals are plotted. On the x-axis is the Big Mac price. Okay, I'm plotting the error. This is a graph that you definitely need to look at. The residual graphs are something that you need to look at. That contains useful intelligence. It can talk about whether it's appropriate model to be using in this situation. It will talk about whether there are any outliers or not. All of that information is contained in residuals. And we will spend the next 15-20 minutes talking about residuals. Okay. So one of the assumptions that we make when you are trying to fit a linear regression model is, of course, that the underlying relationship is linear. That's an assumption we are making, right? Looking at the residuals actually will tell whether that's a reasonable assumption or not. It can help you determine whether that's a reasonable so typically your value of residual, right? This is a residual plot. There will be some numbers that are positive, some numbers that are negative. Is that reasonable to expect? It better be, because if your best fit line had only positive errors, right? When will you have positive errors? If the points are here, correct. So if the points are here and my best fit line is here, then all the errors will be positive, right? Then clearly it's not a best fit line. So a best fit line better have positive and negative things. So the line better be somewhere there. In fact, you can even make a stronger statement. Not only should there be positive and negative values, you should also find that the mean of all of that should be 0. the mean of errors, all the residual values should be 0. That's another thing that you should expect from the best fit line. Okay. If the mean of the residuals is not 0, it means you did an error in your computation of the slope. So you need to go back and do the computation again. So here is the typically this is what will happen. So here is for one particular data set. The residuals are here. Some are negative, some are positive, and over here is the 0 line. The mean value of the residual better be equal to 0. But if the residuals, when you plot the residual shows a pattern like this, then it indicates to you that the original data follows some nonlinear relationship and not linear. Okay, so when you plot residuals, the residuals should not show any pattern. So it should be like this. Residual should be spread out all over. There should be no pattern in it. Why are we saying this? If there was pattern in the residual, it means there is some useful extractable information still remaining in the residual. Residual is something which remains after useful information has been extracted out. If there is a pattern there, it means more information is remaining. What information could be remaining? The extracted linear information. It must mean that the nonlinear information is remaining, right? So when there is a pattern in your residual, it means linear model is not the right model for that data. Okay, so residual information can tell you what type of model you should choose. More things are there, can be extracted. More information is present in the residual plots. Okay, the model that we are using, the linear regression, explicitly assumes that the error terms are independent. That is, one value is not connected to the next value. That's another way of saying that there should be no pattern in there. But also, okay, this chart is just independent stat, so let's finish that. So when the values should be all spread out. If you see this kind of pattern, then it means there is some useful information still remaining in the data. So linear model was not the right model. We need to look at nonlinear model. Okay, and that useful information can be anything. It can be this kind of pattern, or even this kind of pattern. Right? One side is positive, immediately next one is negative. Positive, negative. Right? This is also a pattern. Right? Even here the errors are not independent. So even here, more information can be extracted from the model. So independence of error is one assumption that we are making about linear model. That you are looking at residual plot will tell you whether that assumption was valid or not. Another thing is another explicit assumption we make is homoscedasticity. What does that term mean? It means that the variance, the spread of the error terms should be uniform for all values in your range. Look at this graph. If your residual looks like this, then it means for smaller values, the errors are small. For larger values of your variable, errors are large. This you call as heteroscedastic residual. This is also another example of heteroscedasticity. Here for smaller values, you have large errors. For larger values, you have smaller errors. This is again in some way telling you there is some other information that you haven't extracted out from the data. Okay. Ideally, your errors should be uniform across the plot. When it is uniform, you say the errors are homoscedastic. One more assumption that is made is that the errors are normally distributed. What does that mean? If it was truly a linear model was a good fit, what that means is that some points will be closer to the line, some points will be far away from the line on either side, right? But hopefully more points are closer and you find fewer and fewer points much